So in the previous video, we talked about this idea of a proper standard calibration curve. We said that our standards should be within the working signal of our samples. So if our samples run higher than the highest standard, then we have two choices, and they're on the screen right now. The first choice is to weaken the sample and then rerun it all over again. The problem is that we have to include a back dilution though, so an extra calculation to go back to the original concentration before we weakened it. The second choice was to take a look at our standards, and maybe we need to add a higher standard to the set and then rerun the calibration curve. That way we can include all of our samples into that one calibration curve. The drawback to that is that if we do that, all of the samples have to be processed against the new calibration curve, not just the one or two that may be pegged a little bit higher when we originally ran the samples. So those were the two scenarios that we had. What I want to do in this video though is talk to you more about a calibration curve. And it seems that we have in all of these videos, yeah, that's not a straight line. Am I drunk? So let's say that this is my axis, X and Y, and we incorporate a linear regression line, Y equals mx plus b. And we said in a laboratory, most of our samples or standards, the standards that I run, tend to give me a linear calibration curve. We want an r squared of 1, and the equation looks like y equals mx plus b. And that is true. Most of the time in a laboratory, we are after a linear relationship. So that r squared value is a very strong correlation between the x and the y axis. The issue here, though, is that that's not the only option for calibration curves that I have. Okay, it's going to be very rare, but you could have data that could fit a non-linear curve or relationship. And there is a mathematical representation out there for that data. So what do I mean by that? Well, these are things like exponential curves or logarithmic curves, right? Those sets of data are out there, and they can be experienced and they can be seen in a laboratory. When they do, we try to get out of that arena and we try to modify the x or the y axis to make it linear, but we do try to get out of that arena whenever possible. Sometimes, though, there's no option. We just simply make the deciding factor that this is the way we're going to do a calibration curve. It's going to be non-linear and it's going to fit an exponential curve instead, which is fine. As long as people know the equation, you will be able to solve it just like you do for linear curves. No big deal. So one of the things that we have seen traditionally in the past in the field of UV-vis spectroscopy is that very often we would plot concentration in terms of part per million or molarity or whatever the case. And years and years ago, we would plot a y variable that would be called percent transmittance. And the problem here is that percent transmittance and the concentration, it was not linear. And this was always a problem in the UV-vis spectroscopy world. So what we decided to do is get out of percent transmittance. We didn't like those calibration curves. We didn't like that it wasn't linear. We wanted something that would fit kind of cookie cutter everything else that we were doing in a lab. And we decided not to measure what we call percent transmittance anymore. Instead, we went to a different unit called absorbance. And there's a relationship between absorbance and percent transmittance. Absorbance is actually equal to the negative log of t. So what happened is that we mathematically changed the values of the y-axis. And when we did that, we conformed it to a linear relationship that we were very comfortable with working at that point. right? So whenever we see these types of cases, that's always our first instinct. If we are seeing a relationship that is not linear, can we do something about it? Can we bring in a little bit of mathematics in order to change that number so it can become linear when we plot our curves? Because that's going to be the easiest way to handle the data. So with that said, I want you to understand that sometimes you can actually go in, plot a set of data, and it will maybe be curvy like this and not linear. Or maybe it will kind of trend upward. Who knows? Whatever the case is. These things can take parabola shapes. They can take, all the different variations that you would see in a math course when you learn how to plot an X and Y axis. So that's going to be found in Excel. If I pull up Excel and I bring it over here to the side, you're going to see that show up in the linear regression table. So what I'm going to do is I'm going to click on this chart and I'm just going to delete it. So that way we can kind of do this from scratch. All right. So I'm going to highlight the data again, and I'm going to insert, and I'm going to go to scatter plot, and I'm going to go to plot the points, and that's it. That's all that I want to do. I can visually look at this and see that it's linear, right? So I probably have an idea that it's going to be a linear regression curve. However, if you click on the point and add the trend line, like we've done all of these other examples that we've talked about, you're going to see trend line options right up here, and that's why we have those. So that trend line option, we're almost all the time, every single time, we're probably going to choose linear based on what kind of data that we have. However, if I choose exponential, I want you to look at the graph and see how it automatically changed. Well, if this data fit an exponential line, it would go through the majority of the points, and it does not. So we know that this is not an exponential regression curve, right? Here's the logarithmic curve, and notice the exponential starts here at 0, 0, and it goes up exponentially, right? The logarithmic curve, it does something a little bit different. And here I'm going to get an error. And the reason I'm getting an error is because it says you can't have the point 0, right? 0 is going to cause a problem with the logarithmic curve. So it's not going to show up. But if it did, it would start closer to the 0, 0 mark, and it would basically flatline. There would be some curvature in the very beginning, like it was going to go up, 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 and then it would just kind of flatline after that. So some of the data that we have in the lab could be due to logarithmic data relationships instead of linear or exponential. So if I go back to this main screen with trendline options, we looked at exponential. You can kind of see the example here on the screen. We typically choose linear. There's that relationship. Logarithmic, that's what I was talking about just a second ago. It goes up, 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 and then it just kind of flatlines. I can maybe choose polynomial or the power or a moving average instead. So all of those are my choices. And what you will find out is that on the assignment, or one of the assignments that you will do for this section, it will give you sets of data, and it will go through and ask which set does it match the best. Is it exponential? Is it linear? Is it logarithmic? Is it polynomial? Which one is it going to be? So if I choose polynomial, notice that it tries to make a line that goes through all of the points. And here, this does go through all of the points in a way, right? And if I scroll down and display the equation and the r squared value on the chart, this makes sure that that line goes through all of my points, and here is the equation that represents that. So 4 times 10 to the negative 5th x squared plus 0.0498x plus 0.0125. Notice with the polynomials, my math is going to get a little more complicated. My math is going to get more complicated, and the reason is because we're working with that exponent. So the quadratic equation is going to come into play here. You know, that quadratic equation is probably an equation that your mathematician or your math teacher made you memorize. That had the negative b plus or minus the square root of b squared minus 4ac over 2a. That was the equation. I still remember it from all of these years. But this complicates our math even more. And again, we do not like to go this route. We like for our calibration curves to be simple. We like for our calibration curves to be very bland, and we just want a linear relationship because those are the easiest things to solve for. When I start bringing in x squares and when I start bringing in quadratic equations to figure out what x could or could not be and then checking my answers, we're really delving into areas that could cause us problems in a laboratory. And as a lab manager, they don't want to see that. They want your job to be very simple, straightforward, and clean. They don't want it to have all of these extra math components that's not needed in a laboratory. So for those of you that are a little weak in math, you can kind of take a deep breath because that is what they're looking out for with you as an employee. Okay? So there's the story with the formatting of the trend line, right? Those couple of choices are already built into Excel. Again, you're going to get an assignment that will say, here's a set of data, plot it. Now try to fit a trend line to it and what fits it the best. So it will give you some choices to kind of go by. Is it linear? Is it quadratic? Is it exponential? Is it logarithmic? But you get the idea, okay? So that's what I wanted to say about calibration curves before we go on. Just keep in mind, we keep talking about linearity, but that's not necessarily every single time with every single case, right? We've got some variance in that, but it is the most common type of calibration curve that we have, okay? So good luck on those assignments, and come back and watch the remaining videos for the calibration curves, and you'll get an A. Maybe.